element A of the ring multiplied with minus x is equal to minus ax. This is for all A belonging to R and x belonging to M. A multiplied with minus x is equal to minus ax. So let's have the proof. We know that A multiplied with minus x plus A multiplied with x is equal to A multiplied with minus x plus x. This is by using condition of definition of module, and this is equal to A multiplied with x is an element of the ring. X is an element of the module, sorry, A is element of the ring. X is an element of the module, therefore minus x plus x will be equal to 0 of the module, 0 of the module. And we have proved that an element of the ring multiplied with 0 of the module is equal to 0 of the module. Therefore, A multiplied with 0 of the module is equal to 0 of the module. Also, Ax plus A into minus x is equal to, again use that condition of module, A multiplied with x plus minus x, and this is equal to, again, A, this x is element of the module, minus x is its additive inverse, so x plus minus x will be equal to 0 of the module, and any element of the ring multiplied with 0 of the module is equal to 0 of the module. Therefore, we have proved that A multiplied with minus x plus A multiplied with x is same thing as A multiplied with x plus A multiplied with minus x, and this is equal to 0 of the module. So note that this element plus this element is equal to 0. Again, this element plus this element is equal to 0, and therefore A into minus x is, therefore A multiplied with minus x, this thing is additive inverse of, this is additive inverse of, this is additive inverse of Ax. This is definition of additive inverse. This added with Ax is equal to 0. Again, Ax added with this is equal to 0. So this particular thing is additive inverse of Ax, and therefore A into minus x is equal to additive inverse of Ax. So we have proved that A into minus x is equal to minus Ax. So let's come to another concept. Let me recall our previous work we have done in group theory and in ring theory, and even in sets. When we talk about sets, we talk about subset. When we talk about group, we talk about subgroup. When we talk about ring, we talk about subring. And we have done course on topology as well. When we talk about a topological space, we talk about a subspace as well. So same goes with theory of modules. When we talk about module, we talk about submodule as well. So let's have a definition. So let R be a ring with identity. R be a ring with identity. And M be, capital M be, left R module. Then a subset of M, then a subset, let's write it as N, then a subset N of M is called submodule of M. Submodule, this is the definition of submodule, is called submodule of M if N is left R module under operations induced from M. So all the operations which are for M, those operations will be applied on N as well, and N must form a left R modules under those induced operations. In that case, N is called submodule of M, where M is left R module. So let's have a proposition. This proposition is in fact going to be defining condition for some subset of a left R module being a submodule. So let's see this proposition. Okay, let R be a ring with identity. Let R be a ring with identity. Every ring is going to be with identity. I'm simply emphasizing it. So let R be a ring with identity and M be a left R module. M be a left R module. Then a subset N of M is submodule of M. M if these are the conditions. First condition is N is non-empty. The same condition which you already know from groups and rings. The first condition is N is non-empty. That is, N is non-empty. Second condition is N is closed under addition of M. Second condition is X plus Y belong to N for all XY belonging to n. That is n is closed under addition inherited from m. So this is the second condition, and third condition is ax belong to n for all a belonging to R and x belonging to n. That is n is closed under scalar multiplication. Under scalar multiplication inherited from m. So let's have proof. So first of all, we have to prove that n of m is some module of m if n is non-empty, n is closed under addition, and secondly n is closed under scalar multiplication. So we have to prove that n is submodule. So in order to see that n is submodule, first of all we have to prove that n is abelian group. So first of all we shall prove that n is abelian group. Let me write it in this way. We should prove that n is abelian group. So in order to prove that n is abelian group, we have to show that n is closed under addition, and this is given. So for this, note that we are given that x plus y belong to n for all xy belonging to n. So therefore n is closed under addition. N is closed under addition. Secondly, we have to see that this addition is associative, and associativity is just inherited. Further, x plus y plus z is equal to x plus y plus z for all xy belonging to z, x, y, z belonging to n, which is inherited, inherited from associativity of addition in m, because addition is associative in M, so it is going to be associative in N as well. And the third condition is we have to establish that inverses exist in M, existence of additive inverses. Existence of additive inverses. This is a very important step. How inverses exist? Let's choose an element of N. Let X belong to N. Note that we know that, or we have 1 is in the ring R, so minus 1 is also going to be in the ring R, and therefore note that we are given that N is closed under scalar multiplication. Therefore, since N is closed under scalar multiplication, therefore minus 1 which is element of the ring, scalar element, multiplied with X which is element of this abelian group N, which we are going to prove that this is module as well. So minus 1 multiplied with X will belong to N because N is closed under scalar multiplication. Because of this condition, A is minus 1 and then X belong to N, and therefore minus 1 into X is equal to minus X. Therefore minus X belong to N. So we have proved that if X belong to N, then minus X belong to N. Therefore additive inverses exist in N. Next, we have to establish that additive identity exists in N. Note that mostly we prove additive identity first and then we prove inverses. But in this case, we prove inverses first and then we prove additive identity based on existence of inverses. So, existence of additive identity. Existence of additive identity. Of additive identity. For this purpose, note that we are given that N is non-empty. N is non-empty. So this is the reason we will use. Since N is non-empty, therefore there exists an element X belonging to N. Since it's non-empty, so it has some element. We have proved above that. We have just proved. We have just proved that if X belongs to N, then minus X belongs to N. And therefore, if X belongs to N and minus X belongs to N, then X plus minus X belong to N, because N is closed under addition. This is given. n is closed under addition. Therefore, if x belongs to n and minus x belongs to n, then their sum should belong to n. And therefore, x plus minus x is equal to 0. So therefore, 0 belongs to n. So therefore, n has got additive identity. Now, n is closed under addition. Addition is associative. Additive inverses exist, and 0 element belong to n. Therefore, n is group under addition. Group under addition. And finally, x plus y is equal to y plus x for all xy belonging to n. So this property is inherited. From commutativity of addition in M, and therefore N is an abelian group. So we have proved that N is an abelian group induced under addition induced from M. So this was the first part to show that M is an abelian group. Now, as far as other conditions for being module are concerned, those are just inherited. From M being left R module. So we simply write those conditions also. A plus B, x is equal to ax plus bx. A into x plus y is equal to ax plus ay. AB composed with x is equal to A composed with bx, and identity element into x is equal to x. Also, for all AB belonging to R and xy belonging to N. Also, these conditions are inherited from M as left R module of R. So therefore, N satisfies all the conditions. Therefore, N as a subset of M is left R module of M. So therefore, N as subset of M is left R module under induced operation, and therefore N is submodule of M. N is submodule of M. So we have proved this particular thing. Let's have a note. Let M be a left R module where R is ring with identity. It is always the case. So let M be a left R module. Then note that number one, M is submodule of itself. Every module is submodule of itself. And secondly, just this zero element is submodule of M. So the subset consisting of zero element only is submodule of the module M. Let's have a definition. Let M be a left R module where R is a ring with identity. Then a submodule of M, then a submodule of M other than M, other than M is called proper submodule, is called proper, is called proper submodule. Proper submodule of M. Let's note one small thing, that if M is a left R module, if M is a left R module, which does not consist of zero element only, or zero element alone. Please note that what I am saying is that if M is a left R module which contains more than one element, zero element is always there and then other elements are there as well. So if M is a left R module which does not consist of zero element alone, then this zero, this set 0 is proper submodule of M. And very simple, because M contains more than, M contains 0 and then other elements as well. So therefore, this set which consists of 0 only, this is submodule of M. So this was definition of submodule and a little bit details about that, and then definition of proper submodule. Let's have a proposition now. We have done this proposition for subgroups, for subring, for ideals in fact. If we are given a module and a family of submodules, then intersection of that family is also a submodule. You remember that if we are given a family of ideals, then intersection of that family is also an ideal, and same goes with subgroups. So let's have this proposition that let M be a left R module where R is ring with identity, then intersection of a family of submodules of M is also a submodule of M. So let's prove that. Proof. Let's take the family of submodules of M. So let Ni such that I belong to I be a family of submodules of M. Each of Ni is a submodule of M. We shall prove that. Their intersection over I belong to I, Ni is also a submodule of M. Now note that in order to prove that a subset is submodule, we have to prove three conditions. Number one, that subset is non-empty. Number two, that subset is closed under addition. And number three, that subset is closed under scalar multiplication. So these are the three conditions to be established. We have proved these things before. So first of all, we have to prove that this intersection is non-empty. So this intersection is non-empty because since 0 belong to this intersection, because 0 belongs to Ni for each I belonging to I. Every submodule contains 0. So 0 belongs to intersection of all these submodules. Therefore, intersection of all these submodules, this is non-empty because 0 element is there. So this is non-empty. Secondly, now we take two elements belonging to this intersection. Now let xy belong to this intersection. Xy belong to intersection of these submodules. Therefore, xy belong to Ni for each I belonging to I. If xy belong to intersection of all these, then xy belong to each one of these, and therefore each one of ny is a module, and xy belong to ni, therefore x plus y belong to ni, because module is closed under addition. Therefore x plus y belong to ni, because ni is some module or module, whatever you like, is some module. X plus y belong to ni for each I. And therefore x plus y, since x plus y belong to each ni, therefore x plus y belong to intersection of all these ni's. I belong to I, ni. So second condition is satisfied, that intersection is closed under addition. Number 3, we have to prove that this intersection is closed under scalar multiplication. Now, let A be an element of the ring R and X be an element of this intersection of some modules. Intersection of these some modules. Then A belongs to R, keep it as it is. X belongs to intersection of these submodules, therefore X belongs to each of these submodules. Then keep it as it is. A belongs to R and X belongs to each of these submodules, Ni for each I belonging to I. And therefore A is scalar, element of the ring. X is element of the module. Therefore, their external composition or external multiplication or scalar multiplication will belong to the module Ni. Therefore, A into X belong to Ni for each I belonging to I, because Ni is some module, and therefore now Ax belongs to each Ni, therefore Ax belong to their intersection. I belonging to I, Ni. So we have established all the three conditions. First condition is intersection is non-empty. Second is intersection is closed under addition. And third condition is intersection is closed under scalar multiplication. So therefore, intersection over I belonging to I, Ni is submodule of M. So this was the proof. Now we come to a concept which is very much related to vector spaces. The concept is module generated by X, which is subset of the module. Module generated by a subset of itself. Module, sorry. So module generated by a subset of itself. As motivation, let me give you an example. We know that V, the set of vectors, is a module. This is a module. Set of vectors is a module over R, the ring or the field of real numbers. So we know that V, the set of vectors, is a module over R. Further note that for any vector V belonging to V, we can write V is equal to xi plus yj plus zk. We are talking about vectors in 3 dimensions. Xi plus 1. Any vector in 3 dimensions can be written as xi plus yj plus zk. And note that I belong to this V set of vectors, J belongs to this set of vectors, and K belongs to this set of, because I, J, K are also vectors, so that this set I, J, K is subset of V. So what we are saying is that we have a subset of V such that every vector of V can be written as, we call it linear combination. Every vector of V can be written as a linear combination of I, J and K. Therefore, we have noted that every vector V belonging to V can be written as linear combination. This is what we call it. Can be written as a linear combination of elements of this particular subset I, J, K. Therefore, we say that V is generated by I, J, K. Let me rewrite it. Let let us call X is equal to I, J, K, which is subset of V, and therefore X is subset of V. And what we have said that V is generated by X. Therefore, V is generated by X. So this is the concept